Hi everyone. So in the previous session I have discussed about the concept called AC through pure resistance circuit and AC through pure capacitive circuit, AC through pure inductive circuit. Okay. So before move on to AC through RL circuit, RC circuit, RLC circuit, okay, so let me just revise the phasor diagram of pure resistive circuit, pure inductive circuit, pure capacitive circuit. So in a pure resistive circuit, so we had taken voltage as a reference, so let us call it as Vm is the maximum voltage, and so current also exists in the same line and we call it as Im. Okay, so why both are in the same line? Because it is in phase. So both the waveform alternating quantity of the voltage and the current exist in the same phase. Since there is no angle difference between voltage and current, so we get the phasor diagram in this form. And in AC through pure inductive circuit, so we have taken Vm as the reference one, okay, and remember in a pure inductive circuit current lags voltage by 90 degree. So current lags voltage by 90 degree. So where do we get current then? So here we represent current, which is maximum current, and here the angle difference. So that means to say there is 90 degree angle difference between current and voltage. Of course, current lags voltage by 90 degree. So this is nothing but what? This is nothing but the phasor diagram of pure inductive circuit. And similarly in pure capacitive circuit, so again we have Vm as a reference. Since current leads voltage by 90 degree, so we are going to have Im at this point. So of course here also there is a 90 degree angle difference between alternating current and alternating voltage, but current leads voltage by 90 degree. So this is how we represent in the form of phasor diagram for pure resistive circuit, pure inductive and pure capacitive circuit. Now we shall move on to the next topic, which is AC through series RL circuit. So series RL circuit. So look at this figure, look at this circuit. So this circuit consists of so pure resistance in R ohms and connected in series with pure inductance which is L henries, and so now these two components are connected in series and connected across the supply voltage, which is V. Okay, V is equal to, we know that Vm sin omega t, and the current, so here the same current flows through, resistance and inductance. When the same current flows through these two elements, okay, so there will be two voltage drop. The first voltage drop is voltage drop across the resistor. So let us call this as VR. So V suffix R. So what is the indication of this V suffix R? So there is a voltage drop across this resistance, and there is one more voltage drop. So we call it as VL, V suffix L. So there is another voltage drop that is across inductance. So let us call it as VL. Right, and so here we represent this in the form of vectors. So considering this as a vector now, and even the current, so even the current as vector, and using these vectors, so we are going to analyze this circuit. So how we can analyze the circuit? You know that in a series combination of the elements, V is equal to total voltage, V is equal to, which is VR plus VL. So remember, this is the total voltage, applied voltage. So this can be written. So this total voltage becomes voltage drop across resistance plus voltage drop across inductance. So you can have this equation, and so this equation, according to this equation, so we can have the phasor representation or phasor diagram. So, and here considering now I as a reference. Okay, look at the diagram carefully. So considering now I as a reference. Why I as a reference? Because the same current flows through resistance as well as inductance. So considering I as reference, and if you consider only the relationship between alternating current and voltage drop across the resistance. So you can just recall AC through pure resistance circuit. AC through pure resistance circuit. So what is the relationship between the current, that is alternating current, and the voltage drop across the resistance? So here the phase difference between the current and the voltage drop across the resistance is 0. Since the phase difference is 0, so here this VR exists in the same line. Okay, so I'll just repeat here, since the same current flows through resistance and the inductance, so we have taken current as the reference one, and so here the angle difference between alternating current and the alternating voltage, okay, or the voltage drop across the resistor is equal to 0. So this VR exists in the same line, so that means in phase, right? So this you can just recall from the pure resistance circuit. Now what is the relationship between the same current, alternating current, okay, alternating current with the voltage drop across the inductance? So now you can recall pure inductive circuit, okay, pure inductive circuit. So what is the relationship between the alternating current and the voltage drop across inductance? So here, so we will just recall that current, okay, current lags voltage by 90 degree. So just now I have discussed before this topic. So current lags voltage by 90 degree in a pure inductive circuit. So current lags voltage by 90 degree means to say this VL leads in other way. So we can also say that, right? So current lags voltage by 90 degree is nothing but voltage leads current by 90 degree, right? I'll just repeat the sentence. Current lags voltage. So what voltage? Voltage drop across the inductance, right? So current lags this voltage by 90 degree is nothing but voltage drop across this point leads current by 90 degree. So here at this point, so we can represent this as VL, right? You can see here, so here voltage drop across the inductance leads the current by 90 degree, or we can also say that this current lags this voltage by 90 degree. So lagging means it is lagging behind this side, okay? So leading means that is at the other side. We have represented VR here and VL here, okay, in the form of phasor diagram. Then where do we get the resultant voltage? So now V becomes the resultant voltage. So where we get resultant voltage? So resultant voltage will be here. So this we call it as V. You can just represent it in a dotted line. So this we call it as V. And now if I join this point, because this point and this point, right? So this part and this part same, I can write it as VL, okay. Now look at this, only this triangle. Now look at this triangle here. So now we have VR here, VL and V. So apply Pythagoras theorem. Now we get V is equal to or, so V square is equal to VR square plus VL square. So apply Pythagoras theorem here. So we can have equation as V square is equal to VR square plus VL square, or V is equal to, which is square root of VR square plus VL square. So now we can expand this VR square. What is this VR? It is voltage drop across resistance. That means current into resistor. So now I can rewrite this equation as I into R whole square plus, so VL is nothing but voltage drop across inductance. So remember, I can write this equation as I into XL. So please be careful, it is not I into L, it is I into XL. So we need to express in terms of XL, okay. So XL square. So what is XL? XL is equal to 2 pi f into L. F into L. And so we can simplify this expression. So now if we simplify this expression, so take this I square common. So we can write it as x. Take I square common, we can have R square plus XL square. And so V is equal to, so this square and square root gets cancelled, I into, so square root of R square plus XL square. Okay, and finally this can be written as V is equal to I into Z. Finally we can write this equation as V is equal to I into Z. So what is Z? So remember, Z is equal to impedance. So Z is nothing but impedance, and where Z is equal to square root of R square plus XL square. So this is how we find. Whenever we want to find the impedance, we can have this equation, which is, and this is nothing but the magnitude of Z, which is equal to square root of R square plus XL square. And in complex form we can write Z as R plus J into XL. Okay, so we can also have Z in terms of complex form, so that is Z is equal to R plus J into XL. And similarly we can also find the angle here, which is phi is equal to tan inverse of XL divided by R. Phi is equal to tan inverse of XL divided by R. So in this way we can calculate the phase difference, right, angle difference between the alternating quantities. Now we shall see power in a series RL circuit, right. So till now we have derived the expression and we have understood the concept called impedance, and so next we will move on to the power. And you know that instantaneous power can be expressed as instantaneous voltage into instantaneous current, and instantaneous power is equal to, and we know that V is equal to Vm sin omega t, and I is equal to Im sin omega t minus phi. So to simplify this, we know that sin A sin B is equal to cos of A minus B minus cos of A plus B divided by 2. So according to trigonometric function, so we know this equation, and so simplify this expression using this. So now we can write it as Vm Im, so cos of A minus B, cos of, this is A, so let us treat this as A and this is B. So A minus B, that is omega t minus of this omega t minus phi. So minus of omega t minus phi, right. Okay, now this becomes cos of A minus B minus cos of A plus B. So cos of A plus B means omega t plus omega t minus phi, and this is divided by 2. So I can write here divided by 2, and now in the next step we can have Im Vm divided by 2. And what happens here? So this omega t gets cancelled, so we can have cos of phi. So because minus and minus into minus, it becomes plus, so we get cos phi minus cos of 2 omega t minus phi. Cos of 2 omega t minus phi. And you know that, so we have taken initially instantaneous power. Now to find the average power, so as I have already mentioned in pure inductive circuit, capacitance circuit, right, capacitance circuit or resistance circuit, whenever we take the average power, so it should be integrated. This equation should be integrated. So to get the average power, it must be integrated, and when we integrate this term, anyway this term becomes constant, so the second term becomes 0 if we integrate. So finally P average can be written as VMIM by 2 cos phi. Okay, cos phi, and same expression can be rewritten as P average is equal to Vm by root 2, as we have already did this kind of simplification, Vm by root 2, Im by root 2 cos phi. And so what is Vm by root 2? Vm by root 2 is Vrms, Im by root 2 is Irms. And finally P average is equal to, so straight away I can write this in terms of capital letter. This capital letter indicates RMS value. So Vm by root 2, which is in terms of RMS, capital V and capital I cos phi. So finally average power for series RL circuit is Vi cos phi. So next we have AC through series RC circuit. So AC through series RC. So in the previous topic I have explained about AC through series RL circuit. Now we shall see RC circuit. So here look at the circuit. This circuit consists of pure resistance in R ohms, and which is connected in series with pure capacitance, that is C in Faradays. And so these two components are connected across the applied voltage, which is V is equal to Vm sin omega t, and where the same current flows through resistance and capacitance. And we know that voltage across the resistance can be written as VR, and voltage across the capacitance, so I'll write it as Vc. Okay, so in the next step, how we are going to analyze this circuit? We know that the total voltage. So remember, whenever we consider the elements in series, there will be a voltage drop across each element, and the summation of all these voltages is equal to applied voltage. So based on that, we can write the total voltage V is equal to voltage drop across R plus voltage drop across C. Okay, so remember, total voltage is equal to summation of voltage drop across resistance and voltage drop across capacitance. Now based on this expression, now we can have phasor diagram. So you know that the same current flows through both resistance and capacitance. So we are going to have I as a reference, and of course you know that VR exists in the same line because both are in same phase. There is no phase difference between this current and voltage drop across resistance. Now, so here where should we write voltage drop across the capacitance? So in a pure capacitance circuit, you have learned the concept like current leads voltage by 90 degree. So let me repeat, current leads voltage by 90 degree. So what voltage? That is voltage drop across the capacitance, right? Voltage drop across the capacitance. So that means to say current leads voltage by 90 degree, or else voltage lags. What voltage again? It is voltage drop across the capacitance, which lags current by 90 degree. So that means we are going to have Vc at this point. See, in both the ways we can state this. So current leads this voltage by 90 degree, or else this voltage lags current by 90 degree. So now we have obtained this VR and Vc, and where should we write the resultant voltage? Resultant voltage comes at this point, so we call it as voltage, total voltage. And so since this point and this point is same, see, so this portion is Vc, this portion is VR, and this portion is V. So now we have obtained voltage triangle. So let me rewrite this. So this portion is VR, and this is Vc, and this is V, right? So now apply Pythagoras theorem here. So if you apply Pythagoras theorem, so we get V square is equal to VR square plus Vc square. So which is similar to the previous topic again, and V is equal to, so square root of VR square plus VC square. So remember these terms are in suffix, so V suffix R, and in the next step we can have V is equal to square root of, so what is VR square, which is I square or I into R square plus, and what is VC? So remember VC is nothing but I into XC whole square. So it is not I into C, it is I into XC, where XC is equal to 1 by 2 pi f C. XL is equal to 2 pi f into L, but XC is equal to 1 by 2 pi f C. So let us simplify this expression. Then so we get square root of, take I square common, this becomes R square plus XC square, and this can be, so square and square root gets cancelled, so I into square root of R square plus XC square, and finally we can have this expression as I into Z, right, where Z is the impedance, and Z is equal to, or the magnitude Z is equal to square root of R square plus XC square, and in terms of this phi is equal to tan inverse of XC by R. So we have represented impedance in magnitude, and we have taken the phase, okay, phase, and which is leading, so phase which is leading, and in complex form Z can be expressed as Z is equal to R minus J into XC. Okay, look at the equation carefully. See why it is minus, because we get this VC that is in negative y-axis. Since we have got this VC in negative y-axis, so we get Z is equal to R minus J into XC. But in RL circuit, so we have got Z is equal to R plus J into XL. But here Z is equal to R minus J into XC. So next we shall see a power in series RC circuit, so which is again similar to RL circuit. So instantaneous power can be expressed as instantaneous voltage into instantaneous current. So P is equal to, so we know that Vm sin omega t, and I is equal to Im sin omega t, since the angle, okay, or since the phi is leading, so we are going to have I equation as Im sin omega t plus phi. And so simplify this expression again. So now it is in the form of sin A sin B, which is equal to cos of A minus B minus cos of A plus B divided by 2. Now according to trigonometric function, so we can simplify this expression as Vm Im cos of, so omega t minus omega t plus phi. So omega t minus omega t plus phi, right, minus cos of A plus B. So that means omega t plus phi, and this divided by 2. And in the next step we can have Vm Im divided by 2, and what happens here, plus omega t minus omega t gets cancelled, so you get cos phi minus cos of 2 omega t plus phi, right. So we have obtained instantaneous power. So as I've already told you in the previous topic, so whenever we find the average power, this equation, okay, this equation should be considered for integration, and if we integrate this term, this equation, so we will be getting this part, that is second part as 0. So finally we can have P average, as Vm by 2 cos phi, and similarly P average can be rewritten as Vm by root 2 Im by root 2 cos phi. And so what is the final expression of P average? So P average is equal to V and I. So capital V is nothing but Vrms, capital I is IRMS, and cos phi. We have obtained P average, that is the power in both RL circuit and RC circuit, as Vi cos phi. Thank you.